Okay, good morning. Thank you, everybody, for coming, and thank you so much for Radu for organizing this workshop many years ago. I remember coming here in 2019, and now it's great to come back again in 2024. So today, a quick sort of update on my personal side. So I'm still in Seoul National University in Korea, but I'll be moving to the US. I'll be specifically moving to UCLA. And today I'll talk about a grand unified theory, or my research goal of arriving at a grand unified theory of accelerations. Okay, so let's consider the basic problem of minimizing a convex function f, and of course f is assumed to be L smooth. And the simple gradient descent algorithm, which of course has this one-line description, but I'm going to define this plus notation. So x plus means I'm going to take a gradient descent step at x and arrive at the next position, and the step size is going to be equal to 1 over L. The gradient descent, of course, converges, and it converges at the rate 1 over k under the set of assumptions. Now, Nesterov's fast gradient method has this, using this plus notation, we can describe it in this one-line expression, and it famously converges at rate 1 over k squared. So the modern use of momentum, which is used in, of course, convex optimization, but also quite broadly in other optimization settings where there's not necessarily theory for. So for example, in deep learning, momentum is used quite frequently to make things go faster. This modern use traces back to Polyak and Nesterov. And in convex optimization, momentum does provide an acceleration. So here is the convergence result in terms of function value. Using Nesterov acceleration, we get a 1 over k squared rate. One way to establish this result, one way to prove this result, is to define this energy function uk, where we need to define this zk iterates, where the zk iterates, they don't appear in the algorithm description, at least not in the form that I showed you in the previous slide. It doesn't appear in the algorithm, but it's just something we define for whatever reason. And we've defined this uk energy functions. We show that the UKs are dissipative. And then once you establish this, then we're basically done, because it's the theta k sequence in the Nesterov acceleration. Theta squared is of order k squared. So this can be used to establish the 1 over k squared rate. Yes, so theta is defined in this way. Theta 0 is 1, and then we have this recursive definition. And roughly speaking, theta is k over 2, roughly. So this is a proof that works, and I won't go through the calculations, of course, in this talk, but if you were to sit down and read through the proof, the standard proof, it would take perhaps 15, 30 minutes of focused work to go through all the calculations and verify its correctness. So in that sense, it's mathematically proven, so we understand it. But personally, I don't feel that I understand it. I've written many papers in acceleration, and maybe some of the audience members in this room have a sort of firmer intuitive understanding of the nature of acceleration, but when I do not. And when I read a proof like this, and even when I write proofs like these in my papers, I feel like these algebraic calculations are not transparent. And in my view, the fundamental principle behind acceleration is still unsolved. And some people do share this sentiment. So the problem of understanding acceleration is considered an open problem in machine learning and optimization theory. So, and there has been some work in trying to tackle this, some from like the Berkeley group. But recently, there has been a breakthrough. And the breakthrough that I have in mind is the discovery of several new acceleration mechanisms that are different from Nesterov's. And acceleration turns out to be a much more diverse phenomenon than at least I had initially thought to be. And at this point, I should probably define what I mean by acceleration. So I'm going to give a very rough working definition. So here's a definition. So given a certain setup, there's a simple intuitive algorithm, which is slower. And then there is a slight modification, which complicates the algorithm slightly, but it's faster. It's a kind of definition where I'm basically saying, you know it when you see it. But for the examples that I'll show, I think you'll agree that those do indeed constitute accelerations. So Now that we have more than one acceleration, maybe the various acceleration phenomena, they have maybe a unifying structure. And by finding and characterizing this structure, we'll be able to obtain a more complete understanding of acceleration. Maybe through mathematical abstraction, studying all these things together, we'll get a deeper understanding. So first, let me talk about some accelerations in discrete time, the actual algorithms. So okay, so here are some many acceleration methods. So, FGM, that's Nesterov, OGM, FISTA, but there are some other types, and I've classified them roughly into three types. So Nesterov type, anchor type, the Kim-Fessler type. And these are all quite recent. But there are also others that don't fit under those three categories. So Anderson acceleration, infeasibility detection acceleration, what I call Ball-Pock-Davidson acceleration. These are, I think, different. I haven't been able to think about them too much, but the point is that there are other things, and it's not a clean picture. And the zoo of acceleration seems to be quite diverse. Are they interrelated? I hope they are. And maybe there's we could find a periodic table of accelerations. And maybe we could find a standard model of accelerations where we would organize these things into boxes, and maybe if we find an empty box, that sort of tells us what to look for, and maybe that can sort of advance our understanding of these collection of accelerations. Let me show you a different acceleration. Let's consider the fixed point problem. We want to find a fixed point of a non-expansive operator t. The assumption specifically is that t is 1 over gamma contractive, where gamma is bigger than or equal to 1. If gamma is equal to 1, then t is a non-expansive operator. If gamma is strictly bigger than 1, then t is a contractive operator. The classical algorithm to find a fixed point in such setting is, of course, just to use the fixed point iteration, just repeatedly apply the operator t and hope for convergence. And indeed, if you have a contractive operator, then the Banach contraction principle, it tells us that we do have a geometric convergence. So the fixed point iteration is an iterative algorithm, and it has some sort of starting point x0, and it's a classical algorithm. It's used quite ubiquitously in many engineering areas and applied mathematics. But surprisingly, this algorithm is suboptimal. It's slow, or it can be made faster. And here is the faster algorithm. So this algorithm is we call it OC-Halpern, and it's a Halpern type. It is a Halpern method with a specific Halpern coefficient. So let me describe the algorithm for those of you who may not have seen Halpern iterations. So given the current position yk minus 1, the way we obtain the next point, yk, is we first apply the operator t. We'll get somewhere. And then we form a convex combination, a weighted average between the output of the operator and the starting point of the iteration, the starting point y0. The coefficient of the weighted average is given by this coefficient phi. This phi is an increasing quantity, meaning the weight given to the starting point is getting weaker and weaker as the iteration progresses. I refer to this mechanism as the anchor mechanism because it feels more sort of intuitive. And the idea is that the anchor is placed at the starting point y0, and the anchor pulls the iteration back towards the starting point at a certain strength. And the strength of the anchor diminishes as the iteration progresses. So we can show that this algorithm achieves this rate, and you'll just have to trust me that this factor is smaller than gamma to the power of k. So gamma to the power of k, that's the classical Banach fixed point iteration rate, and this is faster than that for all values of gamma. And in particular, when gamma is equal to 1, then this iteration still has a meaningful rate. So this will reduce to a 1 over n squared rate when your operator is merely non-expansive. And this is faster than the 1 over n rate that is offered by the plain km iteration. So in this sense, I refer to this as an acceleration. I'll just quickly mention that this rate is, so I'll just say, okay, this rate is optimal. There's a matching complexity lower bound, and I'll move on. Here's another setting. We'll consider a smooth minimax optimization problem. So we have a minimax problem with loss function L. L is a convex concave, and the gradient mapping is Lipschitz continuous. And of course, the solution is defined. It's because of convex concavity. We have a sort of clean definition of a solution. A solution is defined as a pure Nash equilibrium as a saddle point. And we'll consider the saddle operator, where we take the gradient with respect to the x variable, which we're trying to minimize with respect to. And then we take the gradient with respect to the y variable, which we're trying to maximize with respect to. And then we put a negative sign over here, because we're trying to minimize it with respect to x and maximize with respect to y. So there's a difference in objective. So the negative sign compensates for that. And also this way, this operator g is a monotone operator. And the solution to the solutions to this minimax optimization problem now is characterized by the zeros of this saddle operator g. So then, before we talk about acceleration, what's the baseline algorithm? Well, the simplest algorithm that is the analog of gradient descent does not converge in general, not under these set of assumptions. So this one doesn't work. The one that does work is the classical extra gradient algorithm. So let me describe the algorithm. So with extra gradient, we start at position zk, and then we evaluate the saddle operator, and we move in the negative saddle operator direction to get to zk plus 1/2. But that's not our next iterate, that's our half iterate. At this point, we evaluate the saddle operator again, but instead of moving in the negative saddle operator direction from zk plus 1/2, we come back to zk and move in the negative saddle operator direction, but with the saddle operator evaluated at zk plus 1/2. And that takes us to zk plus 1. This classical algorithm does converge. And so there's extra gradient, there's Popov's algorithm, there's several other more modern variants as well. And those achieve a 1/k² rate in terms of the squared gradient magnitude. But this can be accelerated. So the accelerated algorithm we call it the extra anchored gradient algorithm, EAG. And it's referred to, it's named so because it combines the anchor mechanism with the extra gradient mechanism. So let's read the algorithm together. So at position zk, we evaluate the saddle operator and we move in the negative saddle operator direction, but we apply the anchor mechanism and we pull the iterates back towards the starting point z0. The strength of the anchor is 1/k plus 2, and it diminishes as the iteration progresses. That takes us to zk plus 1/2. At this point, we evaluate the saddle operator again, and then we return back to zk. And then here we move in the negative saddle operator direction, evaluate it at zk plus 1/2, and then we apply the anchor. That gets us to zk plus 1. So this algorithm, EAG, achieves a 1/k² rate, and it's accelerated. And there's a matching complexity lower bound, so it's optimal. Here's yet another different acceleration, which I refer to the Kim-Fessler acceleration. Let's return to the optimization problem of minimizing f, where f is convex and smooth. But let's measure suboptimality differently. Usually, in this kind of optimization problem, we measure suboptimality with the function value gap between the current function value and the optimum function value. But let's instead consider the gradient magnitude as our performance measure. Now, this is convex optimization, differentiable convex optimization. So this being 0 is the same thing as this being 0. But this being small is not the same thing as this being small. So when we change the performance measure, the optimal acceleration mechanism will change. Let's see. So under this performance measure, what are the performances of the existing algorithms? Well, gradient descent, plain gradient descent achieves a 1/k² rate. Nesterov's fast gradient method achieves a 1/k³ rate. And then Nemirovsky's classical lower bound states that we can't go faster than 1/k². So there's a gap. Is k³ the correct rate, or is k² the correct rate? Well, here's the accelerated method. This method is called OGMG, and it was, of course, proposed by Kim and Fessler. That's why I'm calling it Kim-Fessler acceleration. It very much resembles Nesterov acceleration. So here we have the gradient descent step, and we have the familiar momentum step. The momentum coefficient is different, but it's a positive number. I'll come back to this specific value later, but for now, let's just think of it as a iteration varying a positive momentum coefficient. And then there's this what I call correction term, which is not that important, but it's a positive number. And yeah, so in the form of it, the coefficients are different from Nesterov, but the overall form is quite similar. And this algorithm achieves a 1/k² rate on the squared gradient magnitude. But I said 1/k² is the lower bound. and here we have k squared. So what's going on? The way we obtain the optimal k quadrate is through what I call the concatenation technique, which Nesterov et al. Pointed out. So here's what we do. So the algorithm that I call here's the algorithm FGM plus OGMG. FGM, Nesterov's FGM plus OGMG concatenated. Let me describe the algorithm. So we have a starting point, and we'll run k iteration of Nesterov's fast gradient method. And Nesterov's fast gradient method will return an output. So we take that output, and we plug that in as a starting point of the algorithm OGMG, and then we run a k iterations of OGMG. So 2k iterations in total. Then the output of the concatenated method exhibits a 1/k quadrate. Why is that so? Well, Nesterov's fast gradient method requires an initial bound on the distance to solution, and it provides a terminal function value guarantee. OGMG requires an initial bound on the function value suboptimality and provides a terminal gradient magnitude guarantee. Since the terminal guarantee of FGM and the initial initial requirement of OGMG match, they're compatible. So when we put them together, the 1/k squared rate multiplies out with the 1/k squared rate, resulting in a 1/k quadrate. Okay, so those were 3 different accelerations described as algorithms in discrete time, the real thing. But are they really different? So, and in fact, if we go back a little bit, I classified all these algorithms into 3 different types of acceleration methods. But what was the criterion that I used? Well, the criterion that I used for this classification was to classify them based on their continuous time models. What's the continuous time ODEs, differential equations, that model these algorithms? And if they look similar, then I put them together as a similar type. And this is convenient because continuous time models tend to be much easier to analyze. Okay, so then let's start out with Nesterov acceleration. So Nesterov acceleration famously has this continuous time model. So the way we obtain the continuous time model is we take the algorithm and then we consider the limit of small step sizes. So to be a little bit more precise, that would be in the limit of the L coefficient being driven up to infinity. So this is the continuous time model of Nesterov acceleration. And if we try to interpret it, we can think of this as a continuous time dynamics of a particle with mass 1. So, the Newton's equation is F equals ma. So think of m being written here and x double dot, that's acceleration. But m is equal to 1, so we don't write it. And then the force exerted on the particle is given by the potential that the particle is subject to. So the particle is within a potential given by the function f. And the gradient of the function is the force exerted by the potential. And furthermore, the particle exhibits friction. And the friction coefficient is time dependent. So 3/t, that's the friction coefficient. And now having a time dependent friction coefficient might seem a little bit sort of non-physical, but we're in math, so it's fine. So in continuous time, now things are much easier. So the Nesterov type algorithms have an OD that looks like this or resembles this very much. And if we do a continuous time analysis, we can define an energy function that looks like this, show that it is dissipated by just taking time derivatives, and these calculations are easier in continuous time. And then once we show that this is dissipated, then we are done, basically, because we get an inequality sequence that looks like this. We divide both sides by t, and that yields a 1/t squared convergence rate in continuous time, which matches the 1/k squared rate in discrete time. So this is sort of classical stuff, analyzing Nesterov in continuous time. What about these other acceleration mechanisms? So for anchor acceleration, we can use the saddle operator G as our monotone operator. For the fixed point problem, we need to extract the corresponding maximal monotone operator with these sort of resolvents, but we extract the relevant maximal monotone operator. And here is the differential inclusion that models the anchor acceleration. So think of A as something sort of analogous to the gradient. So this is the dynamics. And if you're unfamiliar with differential inclusions, you can mentally just replace this with an equality. So if you were to look at this just first term, it would resemble gradient flow, just going in the negative gradient direction. Well, we have this anchor term where we pull the iterates back again, or the dynamic back towards the starting point x0, and the strength of the anchor diminishes as time progresses. And now in continuous time, we can sort of carry out a similar Lyapunov analysis. I won't go through it in detail, but because that would take 5 minutes, I don't want to spend that time right now. But the point is, it's a much more easier, straightforward analysis that allows us to recover a 1 over t squared rate, which again matches the 1 over k squared rate in discrete time. For Kim-Fessler acceleration, again, we return to the problem of minimizing function value. We'll measure suboptimality by gradient magnitude. And this is the continuous time model. So ignore the factor 2 because it's not that important. And if you observe this, this is quite interesting, isn't it? Because we have the similar sort of mechanics interpretation. Particle of mass 1 is subject to a potential given by the function f. And the friction coefficient is now time reversed compared to Nesterov's ODE. In any case, sort of just moving forward for the moment, we can define this energy function u, and through some direct calculations, we can show that show the 1 over t squared rate, again matching the discrete rate. Okay, so there's a zoo of accelerations. So what have I done about it? Well, I want to share one result that sort of tries to deal with this mess and try to make connections and try to perhaps reduce the sort of entropy of this entire system. Okay, so the continuous time model of Nesterov acceleration and Kim-Fessler acceleration, they have this glaring symmetry. And as a mathematician, so when I see something like this, I tell myself, this cannot be a coincidence, right? I mean, or at least when I say that, that's perhaps wishful thinking, because I hope things are beautiful and we can prove everything is beautiful. But there's something that is worth looking into quite clearly. So we thought about this, and this is sort of what we've arrived at. So first of all, what we do is we represent our dynamics in continuous time in this integral, I guess, differential equation, where x dot is given by an integral of the previous gradients. So this is an integral from 0 to the current time t, and h is some coefficient matrix, a coefficient kernel. And so basically, our current velocity is somehow given as a combination of the previously observed gradients. Using this representation, so now the h has to be determined, this Nesterov ODE can be represented in this way, and the Kim-Fessler ODE can be represented in this way, where again, there is some interesting symmetry. And we can do this now again in the discrete time setting as well. So in the discrete time setting, the way we obtain xk plus 1 is given as xk minus the combination of the previous gradients. So this is the corresponding discrete time representation. And now this h coefficients, it's a two-dimensional, it's actually a lower triangular array. So we can, it's just an array, so we can put it into a matrix, and we're going to call that an H matrix. And for the OGM algorithm, which is a Nesterov type algorithm, we have this explicit H matrix representation. So the formula is kind of complicated, and I don't want you to pay attention to it. But the point is that we know exactly what the H matrix representation of this algorithm is. And interestingly, OGMG, the Kim-Fessler type acceleration, has this relationship. So, so when you have a matrix, there's the diagonal direction, right? Well, but there's another diagonal direction. So the other diagonal direction is referred to as the anti-diagonal. And if you flip along the anti-diagonal direction, then that operation is referred to as the anti-diagonal transpose. The H matrix representation of this Nesterov type algorithm and the Kim-Fessler type algorithm have this anti-diagonal transpose relationship. You take one of these matrices, you flip it along the anti-diagonal transpose, you get the other one. And okay, so that's an observation of symmetry. So, but then what does this imply? So we established this what we call H-Duality theorem. So Nesterov and Kim-Fessler are dual accelerations in this sense. So the theorem states, let f be a convex function, smooth the convex function, okay, it's a standard setting, and we're going to consider, we have both a continuous time and a discrete time version of the algorithm, but of course the discrete time algorithm is, the discrete time version is the one that really matters. So in the discrete time, we consider fixed at first order methods, and these following two are equivalent. So if we have a method represented by H, so this is the H matrix representation, and let's say we can establish a guarantee on the function value, but there is a certain caveat we need to be able to establish with a certain Lyapunov function. So this is a big asterisk, but I'll just skip over it for the moment. So there's a function, algorithm represented by H has a function value guarantee. Let's flip the algorithm. If we flip it and consider the algorithm represented by the anti-diagonal transpose, the H-dual method, that algorithm has a guarantee on the gradient of magnitude, and these two bounds are exactly the same. So it will be, we want the function value to be less than some thing divided by k squared, something like that. So this bound and this bound is exactly the same. And indeed, the guarantee for Nesterov and the guarantee for OGMG have exactly the same guarantee. And this sort of symmetry relationship explains that interesting relationship. Okay, so let me conclude. There's a diverse zoo of accelerations, and there's been some interesting progress towards systematically classifying and relating them. So this diagram represents my mental model of the state of affairs. So Nesterov acceleration and Kim-Fessler acceleration are somewhat related through this notion of H-duality. Anchor acceleration, due to the limited time, I wasn't able to discuss it, but there's also a nice sort of strong characterization showing that these algorithms are in some sense equivalent. And then there are these other things that I haven't been able to think about, and they're sort of scattered all over the place, but at some point I'll try to get to them and put them into the nice, clean picture, or at least I'll try. So a grand unified theory of accelerations is certainly quite distant. I don't have it yet, but I argue that it's possibly a feasible goal to obtain such a grand unified theory, and whether it's feasible or not, I think it's a productive goal to pursue. And through it, maybe we can gain a much more complete understanding of acceleration. Thank you.